Hey everybody, welcome back. And so what we're going to do now is talk a little bit more about measurements and calculations. So I'm going to talk about a few things. So one thing I want to do is talk about the prefixes and the conversions of the metric system that you need to know, covered in section 1.5 of your book. And then I want to talk a little bit about the English to metric conversions you also need to know, which is covered in 1.6 of your book. And then I'm going to give you a brief introduction to solving problems in chemistry with a technique we call dimensional analysis, and that is covered in 1.7 in your book. Okay, so let's take a moment to sort of review some of the base units that we're working with in chemistry. So each of these base units is associated with some kind of quantity you're trying to measure. And so on the left side of that table, we have 7 quantities we typically measure in chemistry, although we do some of them more than others. So for example, one quantity we measure in chemistry is length, and so the base unit for that is the meter, and its symbol is m. Another quantity we measure is mass, and its base unit is not the gram, it's actually the kilogram, and so its symbol is kg. Again, I'm not exactly sure why they chose the kilogram instead of gram, except that maybe most everyday objects tend to weigh in kilograms, so that may have been a consideration. Another important one is time, which we measure in seconds. The symbol is S there. And then there are a bunch of others. And then the ones that you tend to use a lot in chemistry I've marked with asterisks. So the base quantity for temperature, the unit is Kelvin, and so we'll use that a fair amount. And then also later on, the base quantity of a bound of substance, the name of the unit for that is mole, and its symbol is MOL, so we'll use that quite a bit. Okay, so let me talk a little bit about what prefixes are. So what we think of the metric system is called the System International, and that System International is French for International System, or SI for short. In SI measurements, you will have a base unit like the meter or the liter, and then the kilogram is another base unit. But again, most of the time, you will not be making measurements or even calculations using these base units. And so to give you some examples of that, can you imagine measuring a length of the football field with the meter? So you probably are not going to be using the meter to represent the length of a football field. You may want to use maybe a part of a kilometer. That may be closer to it. Or when I used to work in the lab, the volumes of liquid I worked with were never in, say, 1 liter or 2 liter or a half liter even. They were usually in a millionth of a liter, or something called a microliter. So again, we probably won't use base units that much in the calculations. We're going to be using something related to that. Okay. So at this point, it would be kind of good to think of ways that we could represent multiples of the base unit. So tens of the base unit would be good, 10 times the base unit, 100 times, or 1,000 times the base unit, or even more, or maybe a tenth of the base unit, or 100th of the base unit, or 1,000th of the base unit. So the way we represent those multiples of the base unit is we use something called prefixes. So here are a couple of examples of prefixes. So if we want to say 1,000 of a base unit, we would say a kilogram, for example. If we want to say 100th of a base unit, we would say like a centigram. Okay, and there the base unit being the gram. Okay, so here are the prefixes that you need to know. So what you can see is that the name of the prefix is on the left, and then the symbol is next, and then there's the multiplier, which I'll talk about in a minute, and then there's an example. So for example, you see at the very top, the prefix is tera. And so what tera means, it's basically a shortened word for a trillion. So when you have a tera, you have a trillion of something. So for example, if the base unit is a meter, if you have a terameter, you have a trillion of meters. So 1 terameter is equal to 1 trillion meters. And so we can represent that a little bit with numbers. So 1 terameter is equal to a trillion, which is 1 times 10 to the 12 meters. So you can go further down that list and you can see that there are prefixes for a billion of something, which would be a giga, or a million or something of something, which would be mega, and then 1,000 of something, which would be kilo. So for example, if you had 1,000 meters, that'd be 1 kilometer. So 1 km is equal to 1,000 meters. Or you can write out 1 km is equal to 1,000 meters like that. Okay, so what we've done is we've gone up from the base unit and gone up in multiples of 10. And so we're just getting larger and larger numbers. Now you can go the opposite direction. You can start at the base unit and take 1/10 of that. If you take 1/10 of that, that prefix would be decity. If you take 100th of the base unit, it would be centi. If you take 1,000th of the base unit, it would be milli. Then there's some other unusual ones you need to know as well. If you take 1,000,000th of the base unit, it would be a micro. And if you take 1,000,000,000th of the base unit, it would be a nano. If you take 1,000,000,000th of the base unit, it would be a pico. And I don't know what the word for femto is, but it is 1 × 10⁻15 of the base units. I can tell you that. Okay, so to give you some examples of that, so you're going to be using milli quite a bit. So let's say you want to know how many grams 1 milligram is. And so you would write that out like this: 1 milligram, and then you sort of have to memorize the exponent on the chart. The exponent is 1 × 10⁻3, so you would write 1 milligram is equal to 1 × 10⁻3 grams. If you have a microgram, 1 microgram, you would have to know that that's even a smaller portion of the gram. That is 1,000,000th of a gram, so it's 1 × 10⁻6 grams. And then 1 nanogram is equal to 1 × 10⁻9 grams. So what I'll be doing is I'm going to be solving problems in the near future with these equivalencies. Now, one thing you may note or have learned in the past is that you can say that 1 milligram is equal to 1 × 10⁻3 grams. But also, if you wanted to, you could say that 1,000 milligrams is equal to 1 gram. And so this equivalency is perfectly fine to use in calculations. I think it may be easier to remember this power series here like this. As you get smaller and smaller bits of grams, you have more negative exponents from -3, -6, -9, -12, etc. So this is probably maybe in this form here where you have one of the prefix is equal to the exponent of the base unit. That may be the best way to know it. Okay, and then the final thing you need to know about this, when you're looking at these equivalencies in the metric system, you have to remember that these equivalencies are all exact numbers. So for example, if you have 1 milligram is equal to 1 × 10⁻3 grams, you will have to remember that these numbers, when you're using prefixes from the metric system, these numbers are all exact numbers. So the 1 here from a milligram is exact. The 1 × 10⁻3 is an exact number. And so if that is the case, when you use these numbers in problems and you're doing calculations, if they are exact numbers, that means they will have an infinite number of significant figures. Okay, so moving on. Okay, now one thing you're also going to have to worry about is you're going to have to memorize English to metric conversions. And so I have several there, and this is a listing of the ones you sort of have to know for chemistry class. So for example, I have 1 pound is equal to 453.6 grams. You will note that the 1 in the pound is an exact number, so that would have an infinite number of significant figures in a problem. 453.6, that is not an exact number. So if you have that equivalency and you have 453.6 grams in a problem, it is not an exact number, and you would assume that that number 453.6 has 4 significant figures. Now, on the other hand, the next one down, that's kind of interesting. You have 1 inch is equal to 2.54 centimeters. Both the 1 and the 2.54 are exact numbers. So when you have that equivalency in some kind of calculation, you'll have to remember that both the 1 and the 2.54 are exact numbers and therefore have an infinite number of significant figures. And you can sort of go on down the list. So for example, 1 mile is equal to 5,280 feet. 5,280 is an exact number, and so you should think of that as having an infinite number of significant figures. The next one down, 1 mile is equal to 1.609 kilometers. 1.609 is not an exact number. That is 4 significant figures. Go down to 1 liter is equal to 1.06 quarts. The 1.06 is not an exact number. That has 3 significant figures, but the 1 with the liter is an exact number, and so would have an infinite number of significant figures when you're doing problems. And then the very last conversion, 1 mole of gas occupies 22.4 liters of space. The 1 mole of gas, you should assume the 1 there is exact, an infinite number of significant figures, but the 22.4 liters, you should assume that is not exact, and there are 3 significant figures there. Okay, so now what I'm going to do is talk a little bit about a powerful problem-solving technique called dimensional analysis. So with dimensional analysis, another phrase that you hear associated with dimensional analysis, the technique is also called the factor label method. It's a really nice systematic way of solving problems involving numbers. So when we say systematic, that might indicate to you that this method may be pretty tedious, and it can be at times. But another advantage of having a systematic method is you're less likely to make a mistake if you can do it correctly. So there's some good things about it. So just to give you an idea of how dimensional analysis works, let's just go ahead and take a sample problem where you can pretty much solve in your head, no problem, but I also want to teach you how to solve it using dimensional analysis. Okay, so the problem is this. Let's say you have worked for 8 hours and were paid $10 an hour. How many total dollars were you paid for all of your work? Okay, so first let's do the problem quickly. Okay, so doing it pretty quickly is pretty easy, right? So you're working a total of 8 hours at $10 an hour and you want to figure out the total amount of money you made. So it's going to be what? 8 times $10 an hour. And so you know you made a total of $80. So cha-ching, you're done, right? Okay, so let's solve this same problem using dimensional analysis. So this is going to take a little bit more time, but it's a sort of again, a systematic way to solve the problem, which you can apply to more complicated problems. Okay, so what you want to do is let's sort of look at the problem and look at the numbers that we have. And so one piece of information is that we worked 8 hours. And another piece of information that we have is that we worked at the rate of $10 an hour. Okay. So one thing you can do is if you see a fraction like this, I'm just going to write it in a slightly different way. I'm just going to, you see $10 with a slash here over hour, I'm going to write it as a fraction. I'm just going to put $10, I'm going to keep the unit symbol here for dollars, the dollar sign here, over, and then I'm going to write 1 hour. So note here I don't have a 1 here. We should assume that there is a 1 there. And so we do indicate here in the denominator of this fraction that we have 1 hour. So one thing I want you to sort of know, in this particular problem, you get $10 for every hour you work. Therefore, it's an equivalence in this problem. Again, $10 for every hour, so you can say briefly, $10 is equivalent to 1 hour. That is fair to say when you're solving these kinds of problems. So I set up one fraction from this equivalence. One thing you have to get used to is you're going to have to set up maybe in your mind another fraction. So to create this first fraction, I put the left number in the numerator and the right number in the denominator. To get the other fraction, I do the reverse. So I put the right number in the numerator and the left number in the denominator. Okay, so now I'm going to call this first fraction A and the second fraction B. So I'm going to bring this down here a little bit so I have a little bit more room. So if I have 8 hours, what I want to do is figure out the total amount of money I made in this time that I was working. So what I want to do is take 8 hours and multiply by one of these fractions, either A or B. such that the units in the 8 hours cancels out, and so I'm left with units in dollars. Which fraction would I choose? First, let me do it wrong. So the wrong way to do it is I would choose fraction B. Again, this is wrong. So let me show you why it's wrong. If you have 1 hour here and $10 here, what you can see is we have hours in the numerator and we have dollars in the denominator. So these units, the hours and the dollars, would not cancel. So we cannot use fraction B. On the other hand, we can use fraction A. Fraction A is $10. The units or dollar sign will be in the numerator, then per 1 hour. So you can see hours in the numerator here cancels out with hours in the denominator. And so this is the correct fraction to use. Now, how do you do the math? When you have an equation set up like this with fractions using dimensional analysis, what you do is you multiply all the numerators together, and then when you switch down to the denominator, you start dividing numbers. So in the calculator, you would put in 8 times 10 divided by 1. Of course, 1 is nothing, or it won't change the number any. So it's really 8 times 10. And so here, $80 is what you would receive for 8 hours of work at $10 an hour. So basically, we use dimensional analysis to solve this problem. Okay, let's do another one. The next problem is, let's say that you wanted 36 eggs. How many boxes of a dozen eggs per box do you need? Okay, so do it quickly. So we have 36 eggs, and you know that there are a dozen eggs per box, 12 eggs per box, and you're wanting to know how many boxes are required for 36 eggs. And you probably know, well, there's a dozen eggs per box, 36 divided by 12, and you're going to need 3 boxes, right? So that is sort of the quick and dirty way to solve this problem. But there's another way you can do it by dimensional analysis. So let me do it in that fashion. So let's say you have 36 eggs, and then we have a bit of another piece of information, which is we have the number of eggs per box. 12 eggs per box. Okay, so what I can do is sort of what I did last time is I take this ratio here and turn it into a fraction. So I can put 12 eggs over 1 box. And again, once you see this ratio here or fraction, you can sort of see that for this particular problem, we have an equivalence, that there is going to be 12 eggs per box because you have a dozen eggs in a box of eggs. So we can write out here an equivalence, 12 eggs is equal to 1 box. Now, again, we can write the other fraction. Here in the numerator, we have 12 eggs. In the denominator, we have 1 box. So we switch that. We put 1 box in the numerator and 12 eggs in the denominator. So we'll call the first fraction A and the second fraction B. Now, we're back here at 36 eggs, and we want to know how many boxes do we need to get 36 eggs when you have 12 eggs per box. So the question is this: if you want eggs to cancel out such that boxes is left in the numerator, do you use fraction A or fraction B? It looks to me that you want to use fraction B. Let's go ahead and put that here. So it's going to be times 1 box over 12 eggs. And what you can see is eggs cancels out, leaving an answer in boxes. And so we can do the math. Again, the math, when you're doing dimensional analysis, you multiply all the numerators together, and when you go down to the denominator, you divide by the denominator. So it's going to be 36 times 1, which is 36, divided by 12, should be 3 boxes. So again, this is sort of another problem we can solve with dimensional analysis. We'll be doing more complicated problems in the next talk we have. Thank you for listening.